Hello, so today we are talking about standardizing data and z-scores. Z-scores may be a familiar term that you have heard before. Today we're going to build on our knowledge of them and see them in some different contexts. So this is the problem that we are working with today. As always, you don't need to write down all the words, but make sure you get down those two data sets of ACT and SAT scores. So let's read the problem. It says the University of New Haven admissions office is having a hard time choosing which students to accept. They decide to compare students' standardized testing scores. One admissions officer gathers data from 18 students. Half of the students took the ACT and the other half took the SAT. So there's 18 students. 9 took the ACT, so N equals 9, and 9 took the SAT, so N equals 9. N is just my sample size. So the student who made a 24 on the ACT and the student who made a 1090 on the SAT have the same GPA and amount of extracurriculars. The admissions officer wants to know who did better relative to their test. Was it the 24 on the ACT or the 1090 on the SAT? Can we use statistics to help him figure out who to accept? So the dilemma that we're focusing on is who should they accept, the 24 on the ACT or the 1090 on the SAT? So we are going to compare these two scores relative to their test. So can we use statistics to help them figure it out? Yes, we can. We can use statistics. So standardizing data allows us to compare distributions with different units. So think SAT versus ACT. Those are different units. Standardizing our data, which is what we're talking about today and what section 2.1 talks about, allows us to compare distributions with different units and to measure our relative standing. The standardized score is called a z-score. So how we standardize data is by taking or finding the z-score. So I gave us two formulas for z-score. The first one is the formula in words. So a z-score, or your standardized value, is your data value of x minus the mean from the problem divided by the standard deviation. So that formula in symbols is down here. We say z equals x minus the mean divided by the standard deviation. And the standard deviation, you may see it written as SX. This is the notation your calculator uses. So if you want to make a little note that SX is the standard deviation, that's a great thing to note. So this is how we standardize data. This is our formula. Some of you guys have really wanted formulas because we've been doing a lot with words. Well, here's our first big formula, and we use it for standardizing data and finding the z-score. So what does the z-score help us do? What's the point in finding it? We said it standardizes our data, but the z-score specifically, this is the important definition right here. So make sure you get this down. This is the definition. The z-score tells us how many standard deviations away from the mean the original observation, or x, falls. So the z-score tells me my distance from the mean. How far from the average is the value I'm looking at? So positive z-scores mean the data is above the mean, and negative z-scores mean the data value is below the mean. We use z-scores for normal distributions. We are going to build on what normal means in future videos, but it is capital N normal, and it's a very specific distribution. It's a distribution that looks like this. It's a nice bell curve distribution. So if we look at this little chart we have, this little graph, this plus z means that my z-score is positive because it's above the mean. The mean is in the middle. Positive z-scores mean you did better than the mean or you're higher than the mean, where negative z-scores mean you're lower than the mean or you did below the average that would give you a negative z-score. So who should the admissions officer accept? The 24 on the ACT or the 1090 on the SAT? Well, in order to compare the ACT with the SAT, I need to find the z-score for the 24 and the z-score for the 1090. So my formula is z equals x minus the mean divided by the standard deviation. I'm going to use SX because your calculator is going to use that notation, so I'll just use it for now. First thing I do is plug these 9 numbers into L1. If you forget how to do that, go look at another one of my videos. It was the mean versus median video. It goes through those calculator steps. So I plug these 9 numbers into L1, and when I do, I get that the mean, or x bar, is 24.667, and the standard deviation is 4.416. So I have my x, I have my x bar, and I have my SX, or my standard deviation. Well, now I want to get that same data for my SAT scores. So now I can plug these numbers into the calculator. And when I do that, I get that the mean is 1159.444. So the mean is an 1159.444. And the standard deviation is 116.604. So now I can use this data and this data to find the z-score for 24 and for 1090. So to give us some more space, for the ACT score, I'm going to say z equals x, which is 24, that's my data value, minus the mean of 24.667, divided by the standard deviation of 4.416, and that gives me a z-score of negative 0.15, meaning the 24 on the ACT is 0.15 standard deviations below the mean. It's a negative z-score, and I can see that their score is less than the average for the ACT. For the SAT, z equals x, which is 1090, minus 1159.444 over the standard deviation of 116.604. When I do that arithmetic, I get that z is negative 0.60. So if I think about who did better, who should the admissions officer accept, if I look at these two numbers, I want the higher number. So if I compare being negative 0.15 standard deviations below the mean or negative 0.6 standard deviations below the mean, this is the higher value, so we should accept the 24 on the ACT because it's higher, relatively speaking, than the SAT score. So this is key point number 1. Z-scores tell us the number of standard deviations away from the mean an observation is. The mean we notate as x bar. The observation or the data value is going to be x. The further away the z-score is from 0, remember 0 is my average or my mean. The mean has a z-score of 0, so the more extreme my values are, the further they're going to be from that 0. So we're going to take a look at a NASCAR example. I'm from Georgia, so why not talk a little bit about NASCAR? So we're going to take a look at this example. It says, during the qualifying round of the 2010 Indianapolis 500, Danica Patrick had an average lap speed of 224.2. Remember, the average is my x bar with a standard deviation of 0.7. So standard deviation is 0.7, which is notated as SX or just S. The distribution of her lap speed was approximately normal. This is going to become really important in the next couple of videos. So we're going to go through these 3 questions as we go through the next 3 slides. It says on lap 1, Danica had a lap speed of 223 miles per hour. What is her z-score, and interpret this value? So it tells me her lap speed. It gives me an x value. So right now I have my x bar, or my mean, of 224, my standard deviation of 0.7, and an x of 223. So when I go to find the z-score, I always write the formula, z equals x minus the mean divided by the standard deviation. Well, x is 223, that was her lap speed, minus the mean of 224.2 over the standard deviation of 0.7. That gives me a z-score of negative 1.71. With z-scores, we always round 2 decimal places. I'm going to make a little note. You should make a note. Z-scores, we always round 2 decimal places. So her z-score is negative 1.71. It asks us to interpret this value. So when I go to interpret this value, I want to talk about the number of standard deviations away from the mean her lap speed of 223 was. So when I go to interpret, I would say on this lap, she was 1.71 standard deviations below her mean mile per hour. So on this lap, she was 1.71 standard deviations below her average mile per hour. I know it's below because my z-score is negative. Part B of that same question says another lap, Danica had a lap speed of 225.9. So she went faster this lap than her average. Find and interpret the z-score. Well, I always write my formula, z equals x minus the mean divided by the standard deviation. Her x value is her lap speed, so 225.9 minus the mean of 224.2 divided by the standard deviation. When I do that arithmetic, I get 2.429, but we round 2 decimal places, so I get 2.43. So this is her z-score, 2.43. It's positive, which means she was 2.43 standard deviations above the average mile per hour. Sorry, this is my finger on an iPad, so my handwriting is a little bit poor. She was 2.43 standard deviations above the average mile per hour. So that is how we interpret z-scores. It was a positive number, meaning she's above the average. So part C says, which lap was more unusual? Explain why you think this. Well, we had two laps that we talked about. The 223 lap had a z-score of negative 1.71. The 225.9 lap had a z-score of 2.43. So if we think back to key point number 1, it said the further we were from 0, the more extreme or unusual the observation was. So 2.43 is my z-score. That's more unusual because it's further from the mean, which we said had a z-score of 0. So the further I am from 0, the further I am from 0, the more extreme or unusual my observation is. Key point number 2, when we interpret a z-score, we need to use context from the problem and state the number of standard deviations above or below the mean the value is. So context, remember, that's referencing the problem, and that's super, super important. So lastly, one more little example. It says on the third lap, Danica had a z-score of z equals 0.35. What was her lap speed that lap? Well, if I think about my formula of z equals x minus the mean divided by the standard deviation, I'm given the mean still, I'm given the standard deviation, and now I'm given her z-score. So the piece that I'm missing is her lap speed, or x. So we can use algebra to help us find missing pieces in our z-score formula. So if I think about my formula and rewriting it with the numbers that I'm given, I'll put 0.35 where z is equals x, which is my unknown, that's what I'm looking for, minus the mean of 224.2 over the standard deviation of 0.7. Well, the first thing I do is get rid of my fraction, so I multiply both sides by the number for my denominator. And when I do that, I get 0.245 equals x minus the mean of 224.2. Last step, add 224.2 to both sides. So those cancel. When I add it, I get 224.445 equals x. So on the third lap, she went 224.445 miles per hour. Hooray! So that's a wrap. We can standardize data by finding its z-score. We can use algebra to find the missing variable in the z-score formula. So this is section 2.1 from your textbook. Feel free to go there to look at more sample problems. And remember, in class, we are going to be doing a lot of practice that will help us master this material. So I look forward to seeing you then.